Hi there, you're in the lab with your mate JJ. Today is Maxitronix project day. Today we're going to keep on keeping on with the Sensor Robot 20. It's our Maxitronix kit, affectionately referred to as the 20in1. Today we'll be doing project number 17, which is the low water indicator. So obviously the previous project was number 16, the high water indicator. So this will be number 17, the low water indicator. I'll run you through the instructions on the computer, then we'll duck over together to the booth and put it together. Once that's done, we'll bring it over to the bench and we'll have a look at the circuit underneath the thermal cam, the oscilloscope, multimeter, that sort of thing, just to see how it works. So first things first, let's have a look at the instructions. Here on the computer, so we're going to open up the instructions. Should be here. If this is our low water indicator, I'll just fire that up. Okay, so this is the low water indicator. What it does: in project 16, you use the sensor robot to monitor a rising water level. This project uses the robot to warn you if the water level drops too low. You can use this circuit to check for a low water condition in a tank or in a reserve water supply. Turn on the control and place the touch board at the desired low water mark. This time the buzzer remains silent. Check operation by scooping water out or siphoning off water until the touch board is exposed to the air. The buzzer sounds as soon as the touch board is dry. How it works: when the board is wet, transistor Q5 stays turned on. This is Q5 down here on the bottom left. The voltage at the collector is about 0 volts, and the voltage between the base and the emitter of Q1 is also about 0 volts. When this voltage drops to 0, Q1 turns off. Okay. Q6 cannot operate without the output of the Astable multivibrator, so the buzzer is silent. But if the board becomes dry, no current flows to the base of Q5. Okay. And Q5 turns off. The current does flow to the base of Q1 through the 3.9k ohm resistor to turn on Q1. This causes Q6 to turn on, so the buzzer sounds. Alright, cool. Well, let's pop over to the booth and we'll put this together. Here around the booth. So the first job is to take the wires out of the previous project. Let's do that first. Alright, so that's the wires out, except for the one that we leave here, which is the power supply wire. That's customary to leave. I'm going to take a quick break. I'm going to come back and then we'll wire this thing up. Okay, all the wiring's done except for the touch sensor, which needs to be installed in the terminals here. And actually, speaking of these terminals, they're screw terminals, but they also accept banana plugs, which is really handy. So I was thinking one job we might do first is actually install some banana plugs for our various pieces. This is the voice sensor. And there's a touch sensor over on the bench. So let's put some banana plugs on the wires so we can just plug it in rather than have to screw it in every time. Anyway, over to the bench. Here on the bench. And as I said, the first thing I want to do is install the banana plugs. So let's do that. I'll just put that out of the way. Now I've got a bunch of banana plugs in here. And what we want to do is just put them on here and on here. Now, these are not polarized, so there's no reason to use red and black. So what color will we use? I don't know. Got some screw terminals here. These seem to come with screws in them. So how about 2 green and 2 blue? There's 2 blue, and there's 1, 2 green. And we won't use our red blacks because it's, as I said, because they're not polarized. So we'll put those away. Hopefully we won't need more of them. Depends on if we mess up or not, I guess. Now, okay, I'm not 100% certain that these are going to be strong enough, but I think there's only really one way to find out. Before we put them in, we'll just make sure that they do actually plug in. Oh no, they don't plug in. No, it's not working. Why won't that plug in? Is it too big? I don't know. When I plugged the other one in the other day, it worked. Let me try a different one. What about you? Yeah, that goes in, no problem. Okay, that's interesting. So lucky we checked. Lucky we checked. What are we gonna do? Give me 1 second, I'll be back. Alright, I'm back, and I found this banana cable and this banana cable. Again, the same colors. Let's just see if it goes in. Kind of does. Yeah. Alright. Well, the advantage of these ones is they've got the piggyback, so you can actually stack them. I don't think we'll ever need to do that, but anyway. Now I'm going to throw on the iron because we're about to do some soldering, and I'll break out my H2O, which is actually running kind of low here. I'm going to have to fill that up. Anyway, we'll pour the rest of it in here. Shall we do that together now? Why not? Give me 1 second. So this is my big honkin' bottle of water. It's distilled water, which means it shouldn't have too many minerals in it. And this is my funnel. So, and this is my H2O bottle. So let's just fill ourselves up some H2O. Well, I got some new component drawers installed in the shelf yesterday. I'm pretty happy to have those. Oops, splashed it a bit. Before we pack it all up, I'll just dry up that mess. Dear me, can't take me anywhere. So just top up the sponge there, and fill this guy up again. Alright. Alright, put the H2O away, we're done with that. And I'll put the funnel away when we're finished later. I might keep that water bottle down here where it's handy. Now, some water damage. Alright. Okay, just give me 1 second. Alright, I'm back, and I'm just going to put these banana plugs, which we're not using, back in their case. I feel like if we just forced these, they'd bend, and then they'd adjust and they'd fit in that hole. But I don't like forcing things, and I kind of don't like these banana plugs as much as I like the banana plugs on the other cables, which we're going to be using instead. And that's these. So I suppose once we've installed them, the leads will be really quite long. Alright, well, which one should we connect to which? I suppose it doesn't matter at all. So first things first, let's cut these guys in half. So my snips here. Let's do this one first. Alright, snip. There's no going back now. Same for this guy. Here we go. And snip. Alright, now we're going to need some wire strippers. Got those there. Now we're going to need a bit of solder, which we've got here. Do we need our hands? I think maybe we do. Let's break out the old third hand. So let's take the insulation off. Now I haven't totally decided how I'm going to do this. We're probably going to want some heat shrink as well, just to tidy up at the end. I don't know if I like that. Wonder if we could do better. Maybe. Alright, I'm going to just see if I can do better. I've got these wire strippers as well, which go to a much higher gauge. I'm going to try the 16 gauge. Yeah, well, I think that worked a bit better. Now I've got a box full of heat shrink, so I'll go and grab that. That was 14 gauge, that was the best so far. Alright, so let me grab that wire shrink. Wire shrink. this is my heat shrink. Now if we could get color coded, that'd be good, and it looks like we can, just provided they're big enough. We'll see. So let's try this green one first, see if that'll go over. It will. Okay, great. So we'll put on the two greens. Very good. Alright. And then we'll try the two blues that we've got here. I don't know if they're going to be big enough, but maybe. See how we go. Doesn't look like it's going to fit. No, won't fit. Alright, those blues are no good. What about these light blues? They'll probably do. Alright. So let's do this one first. This is the microphone. I'm not sure if it's a condenser microphone or if it's just some sort of piezoelectric thing. I'm not sure. Just another one of life's mysteries, right? So I'm just planning to sort of hook these around each other and then solder them together. I've dropped a bit of wire here. I don't like the loose wires on the bench because they're a short circuit waiting to happen. Alright, well, pop him around there like that. Alright, now if we put one of these in here, one of these in here, we should be able to hook it together just like that. Alright, and we just squeeze them together. Yeah, I think that'll do. Now we're just going to drown it in solder. So let's do that. Alright. It's pretty good to me. Alright, now we'll do the other one. Alright. Pin out. Pin in. And we'll just tie them together. Alright. And just bend that around. There we go. That ought to be strong enough, I reckon. We'll just use the rest of this wire here. Solder wire, I mean. So I'll hold it with the tweezers. Wonderful. Alright, and I've got a little bit of offcut solder here. I'll put it in the solder offcut straw. Oh, and I found more stray wires. Got them everywhere by the looks of it. Alright. Now I'm going to fire up that that hot air gun. Let's turn him on. Alright, so we're going to want to be doing our heat shrink. Before I do that, let's just put the heat shrink over the top. These joints seem okay. Something's beeping at me. Ah, hang on a sec. That beeping was my air quality alarm. I started soldering without opening the window, and the air quality got bad, and my device alarmed to let me know, so that was pretty handy. I'm a bit horrible when it comes to ventilating the room. Ah, there it goes again. So hopefully that's ventilated enough now and the alarm won't keep sounding. Just putting the heat shrink over the top of these wires. Alright. There we go. So that looks like a pretty good job well done to me. We probably should have put a big black one on here as well. But it doesn't matter much. Maybe some electrical tape. Yeah, I'll just use some electrical tape. I'll put a big black one on the other one though. Learning from experience here. So first things first, let's just heat up the heat shrink. Just going to turn up the temperature on this hot air gun. Put it up to 250. As I said, when I do the next one, I'll remember to put some heat shrink over there so I can finish it off. So we just want some large black heat sink, which we'll go over, and this looks like it'll do. So let's just put that on now so we don't forget. We'll be coming back over these. Alright, so our heat shrink's on for blue, and green is done, so put him out of the way. I'm going to do blue now. Just going to bend this around again. All right. Just take a little bit more insulation off there. Now it was 14 worked for us pretty good last time, so let's do 14 again. Should have done this at the beginning of the project when we first started. We've learned a lot along the way, haven't we? So let's hook that together there. It fell apart. So what did I do with those tweezers? Here. You know, I'm just going to time lapse this, so I'll get it done quickly. Alright, so now we just need to heat up the heat shrink. So get the whole hot air gun, and we'll turn him on. On is good. Here he comes. No. There we go. So let's just heat these up. And what we did with this one that we didn't do with the other one is this extra bit of heat shrink just to round it off. And we'll just heat that up and finish him off. Alright, well I think we're done with our with our soldering iron, so I'll just turn that off once he's cooled down a bit. Alright. So, I suppose we can just test this wiring as it becomes necessary. So we'll be giving the touch sensor a bit of a test. This is the touch sensor, and the I did say I'd put some electrical tape on here, didn't I? I might as well do that together. Some electrical tape here. Alright, well, I'll just start down here and wrap him around. Alright, so one done with electrical tape and one done with heat shrink. Obviously the heat shrink is better, that's for sure, but they're both probably secure enough. So this is the resistor that we need, and this is the microphone that we don't need. So take this away. Now, the other thing to mention is the LED circuit that we use, so that we don't have to listen to the buzzer. So let me show you what I'm talking about. I just left it on the other bench here. You see this circuit's wired in up here to the buzzer, which is here. But the problem with the buzzer is it's noisy and annoying. So what I did was I made this circuit that can use an LED instead of the buzzer. We just need an indicator. It doesn't have to be audible, it just has to be sensible. So let me throw on the old power supply. We're going to power this thing off the bench supply, which is here. So we've got positive here, negative here, and this is our touch sensor, which can go in here and here. Alright. Now, today I don't think we're going to use the cup of water. We're just going to use a wet finger on the resistor. That should do us. Now, this is set for 9 volts. So let's turn him off. And let's turn the power on here. Throw this on here. Okay. And the alarm is sounding, which is what we expected. Now, in this drawer here I've got some alligator jumpers, and I think that's what I want. And we want some female ones. So let's see what we can do about that. This looks right to me. So, oh, look how fortunate. We've got a black on the left and we've got a red on the right. So we've got exactly what we need, which is one black one and one red one. So I think that these alligator clips will be a better choice for us. Let me just move this out of the way while we work with our... how odd. That that black lead has a white shroud on it. Interesting. No big deal, we can deal with that. So let's go here for black. There we go. And here for red. Okay. So we should be able to clip on the LED in the place of the buzzer. So not sure which way around we need to go. Let's try putting that there and this here. And if we throw on the power, what happens? No LED. Okay. So let's just switch the terminals around. Yep. And the LED is on. So we now have a green LED instead of a tone. Now we should be able to change the resistance on this thing to indicate that it's in water. Remember that this is supposed to alarm when the water level goes low. So when the sensor is dry, like it is now, it should be alarming. Its normal state would be resistance. There we go. So I just put my finger on the resistor and it turned the sensor off. And now as it dries out, the sensor comes back on. And it's interesting to see, it's not a binary system, it's a sort of an analog system. You can see that the resistance, a little bit of resistance reduces the light a little bit. You can see just a little bit. You know what I wanted to do with you today was just have a quick look at the resistor itself. So how are we going to do that? First of all, let's turn off this circuit, and we're going to unplug this and this. And I'll just get them out of this tangled mess here. Now this is our touch sensor, which is a variable resistor. And I just want to put our scope in resistance mode and then hook up our probes. One there. There we go, come on. There we go. Alright. So, it's saying really high resistance. Interesting. If we touch it, okay, it's come down to 180. Okay, it's up about 300 kilo ohms. Okay. Now, if we damp the finger, I've got damp sponge, that's handy. Okay, it goes down to 30 kilo ohms. So 80 kilo ohms. Okay. And if we get it It's really, really super wet. Okay, it doesn't seem to go much below about 50k. Okay, so it's about 50k when it's really low. Yeah, okay. What about if we just dead set short it with a screwdriver or something? Let's try that. Let's just short out these tracks here. What about, what do I need? I need some sort of I need a double-ended probe, but I don't think I have one. How will I do this? I really only need a wire. How about this, the solder? So we'll put one end here and one end here, and the voltage comes down. Okay, comes right down to okay, that's what I expected. And then what about if we just short it across these plates? Okay, it comes down as well. Okay, so the voltage, the resistance can get very, very low if you've got enough of these plates shorted. But it looks like the typical low wet reading's about 40k, and anything after that, just as it dries up, the resistance goes quite high. I'm tempted to put that iron back on and dry it out with the iron, but if we dry it out maybe with a Q-tip. So as it dries out, the increased resistance, it's gone up. Okay, it's over a meg now. Okay, and oh wow, it's over 10 meg. Okay, so when it's dry, it's very highly resistive. Interesting. Okay, now we know. I'll put him away. So there is more to do. Just give me 1 second, I'll be back. Okay, I'm back. And I thought the first thing we might do is just jump over to the thermal cam. And see what we can see under the thermal cam. So let's do that. Okay, so that's the thermal cam on the right. There's not much to see because there's no power. So let's power this guy up. Now the alarm is on, the green LED up the back here. And that's on because the low level water sensor hasn't been triggered by a wet signal. And what I want you to notice is the various resistors on the board warming up. You can see that the 1K resistors are all roughly about as warm as each other. When I move my body out of the scene, the hottest point there is 33 degrees Celsius, which is one of the resistors attached to that. Is that Q1? Yeah, it is. Yeah. So the 1K attached to Q1, that's the hottest, but you can see the two hot points here and here. They're the 1K resistors on the Astable multivibrator, and it looks like over here we've got some hot ones as well, which is interesting because they're not as. Oh no, I think it's the 1K, isn't it? Yeah, it is. Let me see if I can just get a better angle on this for you. Yeah, there we go. That's a bit better. So, okay, that one burning bright, that's a 1K as well. Okay, and then the one slightly to the right of it over here, that's a 3.9K. Isn't that fascinating? Their temperature is obviously very highly correlated with their resistance. So low resistor burns more juice. And we can see one up here as well. What are we looking at? Oh, that's actually the LED that's hot there. The LED's hot. Oh no. No, it's the resistor next to the LED that's hot. The LED itself is not hot. And what kind of I wonder what kind of a resistor that is. Let's find out quickly. So let's jump back over here together, and we'll just turn him off, and we'll jump out the old. Shall we? What sort of a Okay. I'm just looking for my LCR meter. I've got a new LCR meter recently, and this is a good opportunity to use it. This is him, and this LCR meter comes with hook clips, which are exactly what we want for this job. So what we're going to do, I'll just get rid of that. Move this out of the way. It's all switched off, but I'll power off the thing as well. Now what we want just quickly is what we want to do is we just want to hook up here. We could look at the colors and figure out what the rating is, but rather than trouble ourselves with that, let's just throw it through the old trusty LCR meter. Now this says resistor 470 ohms. Okay, so so that is the lowest resistance on the board. It's less than 1K. So 470 ohms is what we're dealing with there. All right, so turn him off. Thank you, Atlas Peak LCR meter. Always a pleasure. Let's put this thing back together. Now, if I remember correctly, it wanted positive here and negative here. I'm not 100% sure about that though, so we'll power him up here and here. Yeah, I got it right. Okay, cool. So let's just set up again over here. Now there's more to show you. What else do we need to know? Well, so we did see, and I'm tempted to show you just once more over here on the thermal cam. You can see that the board is the hottest thing. It's hot because I was touching it. So let's throw the power on again, and let's watch this thing heat up. There we go. The resistor's starting to get warm. Everything's warm, warm, warm. I would like to see that 470 ohm resistor become the hottest point on the board. I'll just pull that. I'm just hiding my thermal mass. Yeah, oh no, yeah, okay. So the hot point is jumping around between the 1K attached to Q1, which is 33.2 there, the hottest point. But that's a pretty good showing over there on the LED circuit board as well. Very interesting. I'm just so fascinated to see how the heat is proportional to the resistance. It really is, isn't it? So the 10Ks, they don't burn very brightly, and the 1K is just considerably warmer. All right, now the other thing to look at is the oscillating signal. This let me throw you back over here. Okay, so this part of the board at the bottom here, this is the Astable multivibrator, which sends its output over to one of these transistors over here. I need the schematic. Let me get it. Alright, so Q5 drives Q1, and Q1 allows Q6 to operate. So it's at the base of Q6 where we get our signal. So where is Q6? It's here. Yes. So at the base of Q6, that's where we receive our signal from the multivibrator, and we just need a negative point on the system. Where's negative? Actually, this should be negative. Let's see. Yeah. All right. Now, if we auto calibrate this thing, it's a bit noisy, isn't it? I'll show you. Might as well just show you the whole thing, huh? So this is what we're looking at the moment. It's a bit glitchy. There's a lot of noise down the bottom there. I'm not sure what that's all about. Let's see if we can find a better ground signal. Yeah, I don't know what accounts for that noise that we see at the bottom of the signal there. So that's really quite interesting, isn't it? Why is that happening? I don't know. I want to go, what about measure, add, frequency. Alright. Again, it's the 1.58 kilohertz. That's similar. I think yesterday it was 1.62, which is similar. But we didn't see that noise yesterday, did we? I wonder what would happen. Wonder what would happen if we engage the sensor and try and turn down the resistance. Let's see what it does. Doesn't affect anything really. I have to remind you, this is just the oscillator part of the circuit, so it shouldn't the sensor shouldn't affect the output much. It may. Yeah, right. That's a real noisy signal, isn't it? Wow. So when it gets wet, it goes off. Let's dry it out a bit. There it is, dried out. And as it dries out, the LED comes back on. Just slowly coming back on there now. But that square wave, that's a real mess, isn't it? It's not a good square wave at all. It's not the same as what we were seeing yesterday though. I'd love to understand what's happening around the bottom of that signal there. There seems to be some other signal. Oh, you know what it might be? Hang on. Did that affect it? No. I feel like there must be something in the room that's causing that that interference pattern on the bottom there. Not sure. If you have any ideas about what that noise on the bottom end of the signal is, I'd love to hear from you. I'll throw you back over to the other view. So is there anything more to show you? We've looked at it under the thermal cam. We saw the 1K resistors getting warm. We switched out the cables for some banana plugs. That I think went pretty well. We investigated the resistance range of this thing from about 50K through to several mega ohms. We had a look at the square wave. We've got some noise on the bottom end of the signal that I can't account for. I don't know why that's there. And it does seem to glitch a bit every now and again, doesn't it? Sort of, kind of regularly as well. Let me throw you back over. Let's just watch this signal, and then glitch, 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 glitch. Sort of, it loses the trigger and doesn't reliably trigger all the time. It sort of skips around. I don't know what the correct terminology for skips around is, and glitch. But you can see that that's not a steady, regular signal. That it's kind of missing a beat occasionally, and I can't account for that. I don't know why that would be happening. So there's still obviously more for us to learn, or more for me to learn. Is there anything more to tell you? I don't think so. I'm going to throw you over to the farewell cam and we'll wrap up. And that's a wrap. So, yeah, interesting day. We got a little chore done, which was the alligator. Oh, sorry, not the alligator clips. The banana clips on our sensors. We did one good job, which was this one, and one kind of shoddy job, which was the other one. The reason it was a bit of a shoddy job was I forgot to put the heat shrink on for the overlay, and I had to do it with electrical tape. Not the end of the world. So now we've got banana plugs on our microphone and banana plugs on our touch sensor. So that's all well and good. I think that the circuit worked as advertised. When the sensor dried out, the alarm went on. When it got wet, the alarm went off. That was the expected behavior, so that worked just fine. When we looked at the signal, we didn't see that yesterday, and it was an Astable multivibrator on the same hardware yesterday, so I don't know what's different. I suspect there must be something in the room that's creating that little interference pattern down the bottom there, but I can't imagine what it is. Oh, hang on, what about if I... yeah, okay. I just tried turning off the power supply up the back there. Yeah, that's not causing it. Okay, sorry about that. We're wrapping up. So yeah, we did our oscilloscope, we did our thermal cam, we did our wiring, we put the LED in instead of the buzzer, and that worked just fine. So yeah, I think this circuit is absolutely complete. So I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe. Hi there, look, I'm back. This is just a little addendum to this video. I realized when I was putting together the video that the hookup that I had to test that multivibrator, that was not good. It was not a good idea to connect the base and the collector to get that reading. That just doesn't make any sense. What I've done here now is I've got the base and the emitter connected, and we can see a signal coming across those. Let me just throw you here over to the can I give you a view? You can just see up the top there the signal, and if I bring it in a bit, and the frequency is the same, and the trigger's in the middle there. Okay, so that's what it looks like when the base and the emitter are tested. When it's on, it's active. So that means that there is actually a signal or a voltage for current flowing through the base and the emitter there. If we took the if we took the resistance away, oh no, we'd actually have to short it out, and I'm not going to do that just now. But what I wanted to show you was if we take this off here and we just join these alligator clips and then send this through to ground, and then we'll just recalibrate the scope. This signal that we're looking at now should be irrespective of the of the output here. If I wet my finger and short out the thing, did that change? It did change some aspects of that signal. Interesting. But that's other parts of the circuit affecting the outcome there. So let me just try and dry up this thing again. Alright, that hasn't completely dried up. Why not? I'll just unplug it, that'll do. There we go. Alright, and now I guess the only thing that I really wanted you to see here is that when we've got this connected to ground and we've got the probe on the base of the transistor, then up here, here on the oscilloscope, we do see just a good, honest square wave. But the frequency isn't super regular, is it? If you look at the measure there, it goes from 1.1 up to 2.7, 2.9. I saw 3. So that's that varies over about 2 kilohertz. On the screen, it looks pretty constant to me, that trigger, but the measure is quite variable. So this is not a particularly reliable signal, is it? It's I suspect it has to do with the vagaries of the capacitors and the resistors and this sort of thing. But it is a much more respectable signal that we're looking at now, which is what we'd expect. And there was no reason to expect it was sensible earlier when I had it hooked up. I didn't bring my brain. I wasn't engaged. I hooked the scope up to the wrong pins, and there was no reason to expect it to give you a good signal. Now that it's the base and the ground, then we can see the output of the Astable multivibrator, which is a good solid square wave, but the frequency's a little bit irregular, as indicated by the frequency counter, which is that that box down the bottom left hand corner there called FREQ1. That's the frequency measure 1, and you can see it oscillating around 1.4, 2.4. It's jumping all over the place, which is interesting. You can see it down there. You can't really detect that when you look at the signal itself. Anyway, look, that was just a little extra addendum for this video. Thanks very much for watching, and I hope you have a good rest of your day.